Okay. Um, so we're going to first kind of talk about this idea of a relative rate of change, which is the idea that if we're talking about, let's say we have, $100 stock worth $100 and a $10 stock. And if we look at let's say we have a $10 increase in price versus a $5 increase in price. Increase in price. Well, what would happen here is, once again, let's say I had some money in this $100 stock, a $10 increase. Well, $10, that would be a 10% increase in whatever value of the stock I have. Whereas this $5 increase, since that's half of what the current value is, that would be a 50% increase in value. So even though technically it's a smaller rate of change, I increase the stock by less amount. Since it's on a stock that's arguably pretty cheap, that $5 increase is a much, much, much more valuable increase than what is arguably a larger rate of change of $10. So what we're going to do is not only look at what is the rate of change, but what is the rate of change compared to the actual value that we're looking at. Said another way, when we talk about a relative derivative, a relative derivative in general says we're going to compare a derivative to the actual function value. That's kind of like what we did here, right? This was my change in price compared to the actual price itself. And usually how we're going to talk about a rate of change is with a derivative. Your book, so there's this thing that your book kind of gets into, once again, for those who are really rereading, where it calls this a logarithmic derivative. And the reason for that is, if you think about, it's a very silly way to do it. I'm only covering this so people who read it kind of understand what's going on. I'm never going to define it as this, because it's kind of a silly way to do it. Which is, it says, all right, we're going to let we're going to take the derivative of ln of x times f of x. And if we think about this as a chain rule, the outer function would be ln of u, and the inner function would be just f of x. This would be 1 over u, and this would just have a derivative of f prime. So it would be 1 over f of x times f prime of x. And this technically is the definition we have here, but honestly, I find this to be way more confusing, and honestly, it kind of gets away from what we're actually talking about, which is, this makes a lot of sense, just kind of intrinsically, measuring a rate of change versus the value. Talking about it in terms of logarithms, it's really less a business calc idea, and this is more something you do when you talk about like logarithmic growth, which is more kind of like a physics and engineering type thing. So if you see the term logarithmic derivative, they're really just talking about the relative derivative, but we are honestly never, ever, ever going to use that. Okay. So if you're ever, and then what this is going to do is, like I said, we've written these as percentages. So anytime you're asked to find the percent rate of change, well, that's just going to be the exact same thing times 100%. which is turning whatever that decimal is as a percentage. Okay. So let's look at the following revenue streams. So, given a revenue function, R of x is equal to 100x minus 0.75x squared, where x is going to be in terms of millions of units. R will be in terms of millions of dollars. Find and interpret. The relative derivative at x equals 2. We don't actually have notation for the well, the reason why we don't have notation for it is we're in a relative derivative. Okay. There's not a hard notation for the relative derivative, so usually we'll just say it outright, the relative derivative. So in general, once again, since we're talking about a revenue function, it's going to be r prime at 2 divided by r of 2. So first we figure out what is r prime. So given that r of x is equal to 100x minus 0.75x squared, the derivative here is going to be, well, derivative of 100x is just 100. And then 2 times 75 is going to give me 1.5x. Okay, so we're just going to plug 2 into the derivative. That'll be up top. And then 2 into the actual function itself, and that'll be my bottom term. So working this out, that's going to be 100 minus 1.5 times 2 over 100 times 2 minus 0.75 times 2 squared. Okay, so as a decimal, the actual relative derivative by itself, gives you 0.4924. So this is technically, if you're just asked for the relative derivative, you're always going to get this kind of decimal number. Usually what we'll want to do, so this is the technical relative derivative. Usually what we'll do is we'll turn this, in order to make this an easier interpretation to talk about, we'll turn this into a percentage. So that'll be 49.24%. So what we can say is at 2 million units, actually, no, let me type this out. There's going to be a lot going on here. So this is the relative derivative. This is the percentage derivative. What's the interpretation? At 2 million units, we're talking about revenue, so this is units sold. The revenue is growing by 49.24% of the total revenue. Okay. Questions about this? All right. So this is, like I said, and we can kind of change what these are, but for the most part, this is a relative derivative. Pretty straightforward stuff. There's really not a lot we can do to kind of muck with this. It's just the derivative divided by the function value. These are pretty straightforward. Really, the big thing to keep track of is that technically the relative derivative is always, oops, not what I wanted, is always just the decimal. And when this is technically the percent derivative. So just be careful on the homework, because your homework asks for both of these. You make sure you know the difference. It's really just where's the decimal place. Okay, so the next thing we're going to look at is a pretty big idea in a lot of economics. The idea of elasticity. So we're going to kind of define it very loosely. And then we will get into the actual kind of nitty gritty of how we're going to define it. What does it mean? There will be a formula that's attached to this. So elasticity in general is given a percentage, so given a percentage change in price, what does that lead to as a percentage change in demand? So if, an example would just be, if I change the price by 10%, that leads to how much of a percent of a change in demand? That's kind of the question elasticity is asking. If we have a price change, not just what does it affect the demand, but how much, what percentage, the relative change. And there are kind of two types of goods, what we call inelastic and elastic good. So an inelastic good is when a price change leads to a smaller change in demand. And when we say smaller, we mean relatively smaller. So if we have, something like a 10% change in price, this leads to a 5% change in demand. And actually, I'm going to write these vertically just so I have room to fit everything. So elastic goods, inelastic goods, I should say, are things where a change in price don't necessarily cause a huge change in demand. And these are usually necessities. So an example would be the most common one, like gasoline. Gasoline goes up by 5 cents. You're not going to see a large change in demand because people need gasoline, especially in California. People use their cars to get just about everywhere. So a change in price in gasoline does not really affect demand very much. Now, once again, there's nothing as a good that's always elastic. If there is, there is a price at which gasoline will see, if gasoline jumped up to $7 a gallon, then we would start seeing, yeah, it doesn't matter. At a certain point, you just run out of people who can actually afford that price limit. So gasoline, your utilities, internet is another good example. They're always trying to raise your rate by like $3 to $5 because internet's something kind of you always need, especially nowadays. But if it's a small change in price, you're probably just gonna, eat that because you need that Wi-Fi, you need the internet. I mean, this class, a perfect example of that. So that would be an example of an inelastic good. Okay, so an elastic good would be an example where a price change leads to a large change in demand. So, if we had something like a 10% change in price, that would lead to a 15% change in demand. So a small price change leads to a larger change in demand. So the general rule of thumb, elastic goods are usually sometimes what are also called luxury goods. And these are things these are not mandatory. You don't need these. Big screen TV, fancy new pair of sneakers, high running, a sports, good God, my brain just shredded out for a second. I'm stroking out, sorry. An expensive sports car. Where initially you're like, okay, I don't need that stuff right now. But if there's a price change, the entirety of Black Friday revolves around this idea. If I slash those prices, it doesn't necessarily need to be by a large amount. If there's a 10% decrease on TVs, and if I just advertise that as my Black Friday sale, I'm going to get a lot of foot traffic in on that. So an elastic good tends to be something that is not necessarily a day-to-day use item. It's kind of seen as an extraneous good and a luxury good. Okay. So these are kind of the idea of when we talk about elastic versus inelastic. And then just kind of what elasticity is. It is literally a number that'll tell us, given a change in price, it'll tell us the relative change in demand for that product. Okay, any questions on that? I am kind of boiling this down because we're only going to spend one section. Like some economics books will spend an entire chapter on this entire idea. There's a lot that can go into elasticity. Okay, and the important thing is that it's all based on at a specific price level, right? If gasoline goes from $1.89 to $2.10, that's not going to be as much of a change as if gas is all of a sudden at like $5 and we see a price change to $5.10. There's not going to be a whole lot of drop off here, but there will probably be, once again, once gas starts to get really high up there, small changes will affect people. Okay,
Professor Brown.
Go ahead.
If you give us a problem like that on a quiz or on a test, would it be in like a word problem or just a?
So this is just me bringing up the idea. I have not yet introduced what is the type of problem you're going to work at yet.
Okay.
So this is just kind of, how do we measure this? And that's where the calculus is going to come in. So we're not quite there yet.
Okay.
Okay. So we're looking for this percentage change in price compared to a percentage change in demand. So really what we're looking at is the relative price derivative compared to the relative demand derivative. So if we think about the relative price, that would be the idea of P prime all over P and the relative demand. So when we talk about demand, usually we write this, remember that our demand is usually some function x related to some price function. So we can call that f of P. So we do the relative demand derivative, which would be given by f prime of P over f of P. And the relative price derivative would be whatever my price function is, P prime all over P. Okay, so how this works out, and in general, what elasticity is we're going to compare the change in demand to the relative change in price. So what we're kind of looking at here is, I'll write this up very complicatedly, so f prime of P all over f of P all over P prime all over P. That's technically what this looks like. Now, this is not going to be the final form of this, and some stuff's going to simplify out because we're going to get some nice things that happen. Because technically what we're looking at here is all of these are functions of P. So what we're technically doing is we're taking a derivative with respect to P of everything. So to kind of rewrite this in a slightly different way, and this will start off confusing and then make more sense in a second. So just rewriting these using Leibniz notation of taking a derivative with respect to P. Okay, so my derivatives are only in the numerators of these inner functions. So this is technically a chain, which is we'll take the outer function would be a derivative f prime of P, and would multiply times the derivative inner function, but we're taking the derivative of P as a variable, that's just 1. Okay. And then in the denominator, the derivative of P is just 1 all over P. So I have kind of this top and bottom fraction here. Okay. So just multiplying by the reciprocal, this elasticity function is going to be f prime of P over f of P times P over 1. So that's just going to give me the following function, P f prime of P all over f of P. So kind of describing what these things are. Here we're looking at, this is the price. Here we're technically looking at the change in demand, slope of the demand. And this last one, we're just looking at what is the actual demand itself. Now, if we kind of think about this in terms of sign, price is always a positive number. You can't have a negative price. Demand is also something that is always positive. And change in demand, we've talked about this before when we talked about any sort of demand curve will always have a negative slope, always. because as you increase the price, you decrease demand. So this is technically going to be a negative number. So overall, if we left this number as it is, this would always give me a negative number because price is always positive. The change in demand is always positive. Is always negative, and demand is always positive. So if we multiplied all these together, positive times a negative divided by positive would always give me a negative value overall, which can kind of be a little confusing because we want to talk about this in terms of a relative nature. So what we do is elasticity. To solve that problem, we just slap a negative on this thing. And this is your actual function for elasticity, E of P. So this is what you're going to be plugging into. So we have this negative that's kind of inherent because it's just going to make this a number that's always positive. Okay. So this is the kind of the thing you need to write down, have in your notes. This is the formula we're going to use. Okay, so let's do an example with one of these. Given a demand function, x equals 500 times 20 minus p. We're going to go through a couple parts here. Part A, find the elasticity function E of P. Okay, so technically right here, even though this was given as an x equals, this is technically my price function, my F of P. So once again, E of P in general is negative P times F prime of P all over F of P. So just doing a little bit of work off to the side. Here's, F of P is already given. 500 times 20 minus P. And the derivative of that, well, 500 is just a constant, so we can bring this down. The derivative of 20 is just 0. And the derivative of minus P is just minus 1. So F prime of P is just negative 500. So if we plug in here, we're going to have negative P. F prime of P was negative 500 over F of P, which is 500 times 20 minus P. And what's going to happen a lot with these is there's usually going to be some simplification you can do to cancel some stuff out here. In this case, we can cancel out the, so then, well, what the heck, I'll write this all the way through. That'd be negative and negative would be positive 500p all over 500 times 20 minus p. 500s cancel. And here we have our elasticity function. Any questions on that?
And the p's cannot cancel out, correct?
Correct, because that subtraction there, we can't break up a subtraction in the denominator.
Okay, thank you.
Okay, now to actually use this thing. If you plug in a number, what the hell does this actually tell us? So, interpret E of 4. So first of all, we'll plug it in. E of 4. This is just saying P equals 4. We're just going to plug that in. So that'll be 4 over 20 minus 4. So 4 over 16, which will give us 0.25. Okay, so there's a lot going on here. And what this is kind of like the conversion rate. This is telling us that whatever our change in price is, there will be a 0.25 relationship between the change in demand. Said another way, let's actually give this a number. Let's say we had a 10% change in price. What that would give me is 0.25 times that 10%. So 2.5% change in demand. What this 0.25 represents is kind of what is the conversion rate. If I had a 10% change in price, and once again, this is at a price of $4. If we change the price, we change this ratio. But this says at $4, whatever your price is, whatever your change in price is, your change in demand will be 1/4 smaller. So a 10% change in price would be a 2.5% change in demand. And that's what this elasticity measures. It's what's the ratio? What's kind of the conversion rate between your change in price to your change in demand? And if we went more specific, if we said so this is just a general change in price. If we talked about a 10% price increase, well, we could also say, once again, it's a 0.25 times 10%. So that'd be 2.5%. Since we increase the price, that's going to be a decrease in demand. Because once again, price and demand always go in opposite directions. Questions about this? Okay. So technically speaking, what we have here is, once again, we had a change in price led to a smaller relative change in demand. So this would be an example of, this would be inelastic. At this price, my good is inelastic. A change in price led to a smaller change in demand. Okay, let's do one more. Let's look at E of 16. So I'm just going to plug back into my function. So that would be 16 over 20 minus 16, which gives us 16 over 4, which gives us 4. So once again, this number represents the conversion rate. So if we still had that 10% change in price, Well, now a 10% change in price is going to lead to 4 times that 10%, or a 40% change in demand. So here we have an example where a change in price led to a bigger change in demand. So this would be an example of an elastic good. So again, we're talking about the same price because both these we're talking about the same product, is what I should say. What changed here is we went from a price of $4, that's what P stands for, our price, to a price of $16. If we're talking about something like, let's say, a cup of coffee moving from $4 to $4.40, not that big of a deal. But if we're talking about $16, that must be a hell of a cup of coffee, and any change in price is going to lead to a much larger change in demand. Okay, questions about this?
Would it still be implied that the 40% change is decrease?
Well, so notice I just said a change in price. I didn't say what direction,
Yep.
right? So if
Right.
we said, let's say a 10% decrease in price would lead to a 40% increase
Decrease. Okay.
in demand. So increase, decrease, if we just talk about change, we're only stuck talking about change. If we say what direction that change occurs, then we can mirror that to talk about the change in demand. Okay, questions on this, anybody? Okay, so there are kind of three cases, which is, once again, we talked about the idea of being inelastic, elastic, and then we have a third one, which we call unit elasticity. So inelastic is anytime we get this function to be between 0 and 1. And this is what happened so basically you get a decimal in between 0 and 1. And that's what we got in this problem part B, right? That 0.25 means that there's a smaller change in demand compared to the relative change in price. So if you get a decimal in between 0 and 1, that's inelastic. Elastic is anytime you evaluate your elasticity function and you get a value greater than 1. This is what happened in part C here. We got an elasticity value of 4. So that tells us that my change in demand is always 4 times greater than my change in price. So that's elastic. Unit elasticity is when this thing equals 1. And this is where we haven't discussed this as an idea, but the idea of unit elasticity is that it's an equal change. If I have a 10% change in price, that leads exactly to a 10% change in demand. That's unit elasticity. We're not going to do a lot with unit elasticity. Usually what we're going to do is we want to break our function down into where is it inelastic and elastic. So usually what we'll do is we'll break it down by, we figure out where it's unit elastic, and then everywhere below that it'll be inelastic, everywhere above that it'll be elastic. So usually this last one, the unit elasticity, is something that we set our equation equal to and solve, and that gives me a price point at which we switch back and forth. In fact, you know what I might just do is I'm going to put this guy in between, because usually it is a price that is in between inelastic and elastic. Okay, so let's do another example. All right, so given some price function fp is equal to 40,000, oops, 40,000 minus 1,000p. Find all intervals where the good is elastic and inelastic. And actually, let's just say find all intervals, we'll say of the price, to be very clear what we're doing intervals of. Okay. Okay, so we're still going to go back and do our elasticity function. So E of P, it's negative P times F prime of P all over F of P. So real quick, finding F prime, just the derivative of this, which is just 0 minus 1,000, so it's just negative 1,000. Okay, so just plugging that in. So my elasticity function is negative P times negative 1,000 all over 40,000 minus 1,000p. Oops. So negative P, negative 1,000, so we have 1,000p all over 40,000 minus 1,000p. So once again, like I said, a lot of times there's going to be a common number that you can factor out of all of this. This is technically just fine, but let's make our life easy, make these numbers a little bit smaller. Both of these I can factor out 1,000. And that'll just leave me with 40 minus p. And now we have our elasticity function. Okay, so we want to find the intervals where we are inelastic versus elastic. And so what we want to do is usually what we'll do is we'll figure out where is my good, where does it have unit elasticity? And then from there, we'll just say everything below will be inelastic and everything above will be elastic. But we're going to always do this unit elasticity. Well, unit elasticity happens when my function equals 1. That's going to be kind of this breaking point between an inelastic versus an elastic good. Okay, so really we're just solving this little algebraic equation. So, cross multiply, and that gives us that P is equal to 40 minus P. Add on over, 2P equals 40, so P equals 20. So this is that price at which we switch back and forth between elastic and inelastic. So in terms of the intervals, well, we're talking about price, right? This is a $20 price. The lowest I can set my price to be is $0. So we're inelastic on the interval from 0 to technically 0 to 20. And we are elastic going to the right. So yeah, we're inelastic going to the left, elastic going to the right, which is 20. Now, here's the thing. It looks like this line just goes on infinitely to the right, but we need to kind of think about this. This is, once again, this is my price model, right? And there becomes a certain price at which no one will buy my good. If I keep raising the price again and again and again and again, eventually I'm going to hit zero demand. So kind of, it looks like it goes from 20 to infinity, but that's really not the case. Because at a certain price level, we're going to just stop getting people who are willing to buy my product. So how do we find that number? Well, it'll be whenever we hit zero demand, right? So there are a couple ways to think about this. One, it could be, remember, this is technically the demand equation. You could just set that equal to 0 and solve for that price. But what's also easy is remember that this here is also the demand. These are the same functions. So what you can just do here is once you get this elasticity function, if you want to figure out where do we have, once again, let me write my elasticity function. Where do we top out? What you can just do is once you have this function, just set your denominator equal to 0 real quick. And then you'll just have 40 minus p equals 0. So the price we top out at is $40. And there we have the interval for which my good is elastic. And this is once again the intervals of price. So one more thing we're going to talk about is how does elasticity affect revenue? There's a very simple explanation here, but to kind of get into that, remember that when we're talking about revenue, we're talking about the number of units times the price, or remember we're talking about the demand times the price. So if we are inelastic, remember what that means is that whatever your change in price is will have a smaller change in demand. So if we had an example where, let's say, if we were inelastic, if we had a 10% increase in price, but only a 2% decrease in demand, well, we increased the price more than we lost. We increased the price more than we lost. So this is overall a net increase in revenue. If we are elastic, well, if we have something like a 10% increase in price, That would lead to a larger, let's say 18% decrease in demand. This would be a net decrease in revenue. So what we're saying here is that if you're inelastic, a price increase increases revenue. If we are elastic, if we still want that same net thing where we increase revenue, we need to go in the opposite direction. We need to decrease price in order to increase the revenue. Okay, so you have a couple of these on the homework, which is based on this. We'll say, if we want to increase revenue, what should we do? And the short answer is, if we're inelastic, we want to increase the price to increase revenue. If we are elastic, we want to decrease the price to increase revenue. Does that make sense? Questions on that? So the question then becomes, well, okay, what happens if we're a unit? And it turns out that is when we actually hit our max revenue. So that price, remember that when E of P equals 1, that is the price at which max revenue is achieved. Okay. Question on this so far? All right, so let's do a slightly harder function for demand. We'll kind of go through a couple questions. Given that D of P is equal to the square root of 150 minus 3P. Part A, find the elasticity at a price of $38. Okay, so remember that what we're going to do is take negative P times the derivative here, all over the original function. So this one doesn't have such an easy derivative, so we're actually going to work that out a little bit separately. So the bottom's going to stay the same, square root of 150 minus 3P. And then up top, okay, so once again, I'm going to rewrite this as a 1/2 power, so 150 minus 3P to the 1/2. And then we're going to break this up using a chain rule. So the outer function is u to the 1/2. The inner function is
Professor, it might just be me, but I can't hear you. Can everybody else hear him?
No, mine went mute as well.
Can you guys hear me now?
Yes.
Great. Okay. Sorry about that. Yeah. Every now and again, my program crashes and it doesn't tell me that it crashes. So, where'd I drop off? What was the last thing you heard me say?
When you started taking that u to the 1/2 and then you kept writing it, I can hear you.
All right. So all we're doing here is we're taking a derivative using a chain rule. So we're breaking this up into, first of all, we rewrite this as a 1/2 power. And then we are just going to take, actually, I'm going to slide this over just a little bit. So we're going to break this up into u to the 1/2 and u, which is just 150 minus 3p. And we're just going to take our two derivatives. So our first derivative of this first piece would be 1/2 u to the negative 1/2. And so that's just 1/2 times the square root of u. And the derivative of the bottom here is just going to be -3. So this is going to be multiplying together 1/2 square root of u times a -3, or rewriting this as -3/2 times the square root of 150 minus 3p. So kind of just doing this off to the side for the derivative part. Questions on that derivative? All right, so technically speaking, we could slot that in right here, but what's going to make it real easy is actually, I'm just going to multiply it here on the right-hand side, which is totally valid algebraically. Because something wonderful happens, and here's our elasticity function. We get a -p times a -3, so that's 3p. And then the square roots cancel out, so we just have 2 times 150 minus 3p. Questions on this, anybody? This is finding the elasticity. The derivative here was a little bit harder to work out. But any questions on this so far? All right, so now from here, we're just going to plug in $38. So it would be 3 times 38 all over 2 times 150 minus 3 times 38. So you get the value of 1.583. So the question is, find the elasticity. We did. And since this number is bigger than 1, that tells us that we are elastic. Part B. To increase, how do I want to say this? What should we do to the price? To increase demand? Demand. And this goes back to what we kind of said earlier, which is anytime we're elastic, if we want to increase demand, this is a real simple one. We just shoot out, we need to decrease the price. All right. And then part C. Find the price that maximizes revenue and the max revenue. Oh, maximizes revenue and the max revenue. Okay, so the max revenue happens at unit demand. So we're going to set our elasticity function and set it equal to 1. And that's going to give me the price. And then we'll talk after that how to get demand. So once again, my elasticity function was 3p over 2 times, I believe it was 150 minus 3p. We're going to set that equal to 1. Do a quick little cross multiplication. And just solve this out a little bit. So 3p, if we distribute, that's going to be 300 minus 6p. And then if we add over, that's going to be 9p is equal to 300. So lastly, divide by 9. And that gives us $33.33. So at that price, we're going to have maximum revenue. All right, so the next question is, what is the max revenue? So this comes back to the idea that revenue is equal to, well, it's however many units I'm selling, the demand times the price. So we have a function that we were given for the demand. My demand function based on the price P was the square root of 150 minus 3p. So there are kind of two ways to think about this. One is very, like, there's an algebra way to think about this, which is in general, the revenue is just going to be this demand function times the price, which we're just going to call P. Because this is going to tell me how many units we're selling. And this is telling me at what price are we selling those units. So all we're going to do is just take this equation and we're going to let the price equal $33.33. And that's going to give me my max revenue. So we finish this up. And you get a max revenue of $35.70.
Professor, and for that the 3 times 32, 33, we can just assume it's gonna be 99, correct?
Yeah, if you want, you can round. I mean, technically it'd be 99.99. So if you want to round it up to 100, feel free.
Okay. All right, thank you.
Yeah, feel free. Okay, other questions? All right, folks. That is going to do it for class today. As always, if people have any questions about anything, I will stick around. If not, have a lovely evening and a good weekend, and I'll see you back here on Tuesday. Just remember that we do have our quiz tomorrow covering the homework that's due tonight. Otherwise, goodbye, everybody.
Thank you, Professor. Good night.
Thank you, you too.